Yes,
Yep,
sir.
good deal. All right, so as you all know, we're winding down. I think we got 2 more weeks. Um, 2 more weeks of classes. Let's see, this week, next week, and the week after. So 3 more weeks of classes. And I would usually I have a final project, but I'm not, yeah, I don't really like it. So what I'm gonna probably have you do is write like a little short paper on a launching device. Just kind of like what you all did with the history of engineering. You'll just do a little quick research on a launching device, the history of launching devices, what they were used for, things of that nature. I'll send out an email, something quick, just because the final project, I'm not, yeah, I wanted you guys to design something, but we don't really have time. Um, your winter break kind of like messed everything up. I had been thinking about, showing you guys how to do some modeling, though I wasn't going to have you model it. But needless to say, I'm just going to have you guys do like a little research on launching devices. And then just you could do that as just a little group assignment. And I'll get it all orchestrated. I'll assign it this Thursday. I don't want you going too in depth with it, but just look at it in terms of like if you were going to design it, but just from the research standpoint, and then I want you to just write a paper on your research, and it'd be like a report more so. It'll be like a lab report. Um, so today we're going to be going over chapter 11. Um, another one of my favorite chapters. I won't hold you too long. We won't cover all of it because again, it's a lot to cover. Uh, but any questions? No. Okay. There's my book. All right, good deal. So we're gonna have a couple examples. So hopefully you got your books open. But today, let me pull it open. Today we're gonna cover temperature and temperature related variables. Temperature and temperature related variables. So I had a discussion that I assigned. I'm not sure if you all have touched it yet, but it's okay. We will cover it in class. But how is temperature used in engineering? So, for mechanical engineers, you're going to use this heavily, right? Well, how temperature is used in mechanical engineers. How many of you all like computers? Some of you, not many of you. Patrick, all right, all right. What's the most important thing about your computer to keep it running? The fan, keeping it cool. Absolutely. Y'all are right on point. And so, what would that be called? From a mechanical engineering standpoint, what would that be called? If you probably don't know, but maybe you do. There you go. Heat transfer. So, that's what we're going to be covering. So, from your own, I don't know, I guess your own, just from your own definition, in your own words, what would you consider temperature to be? In your own words, what do you consider temperature to be? The amount of heat of an object or thing. All right, that's good. Looks like, did you read that out of the book, Lawson? Oh, that's good. Anyone else? Hot or cold? So the measurement, how hot or cool something is. That's good. That's good. So just two people. Okay, well, cool. All right, that's what's up. Okay, yeah, yeah, yeah. All right, now you're getting into more how many molecules are vibrating, right? So that's going to basically determine how hot or cold it is. The faster they are, the hotter something is, the slower they are, the more at rest your molecules are, the colder it is. All right, that's good. So let's talk about it. Let's talk about temperature. If I can find it, what did I do with it? I think it disappeared. Oh well. All right. So again, let's talk about temperature. Temperature is one of the seven fundamental or base dimensions that we use to properly express what we know of our world. Base SI unit. Kelvin, obviously, we've talked about this before. Celsius, right? And then imperial Fahrenheit, of course. But temperature, understanding what temperature means and what its magnitude or value represents is very important in understanding our surroundings, right? We need a physical quantity. The final project is a group thing too. Yes, right. The final project is a group thing. We need a physical quantity or physical dimension to describe how hot or cold something is. So when you look at the role of temperature in engineering design, developing a good understanding of what it is meant by temperature and how it is quantified is all necessary in engineering disciplines. So let's talk about temperature. I can't see my slides anymore. Oh, there it is. Here we go. So temperature is a measurement, right? That's what temperature is. Temperature is the measurement of the object, more or less, right? And so it represents the level of molecular activity, as Hunter pointed out, uh, provides a measure of molecular activity, as Cassandra pointed out. The molecules of a substance at a high temperature are more active than at lower, right? So what's the difference between temperature and heat transfer? Nobody knows.
Is temperature like the temperature of like an object, and heat transfer is how much it's like radiating off or onto something?
Yeah, that's close, pretty close. Yeah, yeah, I like that. So temperature basically denotes how much heat has transferred from or to an object, right? Like the temperature, because you will know how hot or cold it is, right? And then heat transfer is the amount of energy either gained or lost from that object. All right. So when you think about heat transfer, you think about energy. When you think about temperature, you think about the measurement of that energy, not in a sense of I'm measuring the energy. It's in a sense of heat, right? Or how hot or cold it is, right? So when you look at temperature, I'm not sure if that made sense, but when you think about temperature, think about the measurement of how hot or cold something is. When you think about heat transfer, you look at how much energy is gained or lost of that particular something, right? So if you're an object, me personally, an object, and then I put a fan on me, Right? And I'm blowing off that heat. So I'll have a starting temperature, and then I put a fan on me, and then I'll blow off the heat, right? And then I'll become a lower temperature. Right. So the heat transfer was the difference between my starting temperature and my final temperature. There was a heat transfer. So what was the heat transfer? Well, you have to calculate that using the work done from the fan plus, or not plus, but in times, I don't know if we have some type of a heat transfer. There's a heat constant, which we're going to get into for heat transfer later in these slides. But there's this quantity, and then so we'll have to figure out how much how much that constant quantity is for my body, right? To determine how much energy changed from when I was hot, and then when I put the fan on me, and then when I became cooler. And so temperature just basically measures just basically the difference. Temperature is just the hot or cold state that I was in. Hopefully I didn't confuse you too much. So ways to measure temperature. What do we use? What are some things you would use to measure temperature?
Thermometer.
Thermometer. What's another one?
That the laser thing.
Right, like a laser, absolutely.
And then there's the thermal like radar, like camera. Like, I don't know how to put it.
So the laser would be something similar to that. Another one would be a thermocouple. Right. And so, and then you have a thermistor. Let's see. Then you have different types of thermometers. Not thermometer, but different types of thermocouples. I'm jumping ahead in my slides. Let's see. Where we at? And so, do you all know what? I'm not sure if you all have any dealings with thermocouples. No. Okay. So you use thermocouples, and so you have different thermocouples for different ranges of temperatures. And then obviously you all know about thermometers. And back in the day, you used to use the mercury thermometers. You don't use those anymore because of the mercury is poisonous. And then so this is all stuff that we've already discussed, like temperature relationships among temperature scales. So I won't go into that. We've already done things of that nature. But let's jump into heat transfer. All right. So temperature difference in heat transfer. Heat transfer, a form of energy transfer that occurs between bodies of different temperatures. Heat always flows from, keep this in mind, heat always flows from a high temperature region to a low temperature region. It always flows from a high temperature region to a low temperature region. All right, keep that in mind. And so we also have, because it's energy, right? You have your units for energy, which is BTU, calorie with a lowercase c. All right, and then notice there's also uppercase C calorie, which is also for energy, but it's usually used for food. So you'll see an uppercase C on your labels when you're looking at eating, when you're looking at food. All right, the lowercase c is energy that's used for heat transfer. All right. And notice it's uppercase C calorie is equal to 1,000 lowercase c calorie. So keep that in mind as well. These are just the conversions. All right, so let's get down to the nitty gritty. Conduction, convection, and radiation. These are the three types of heat transfer. What is heat conduction? Anybody know? What is heat transfer? Not heat transfer, I'm sorry. What is heat conduction? Yes, it's a way heat transfer is transferred, but it's what is that particular way when you're looking at conduction? Two solids touching, absolutely. So somebody's been reading. Somebody has been reading. So conduction, a mode of heat transfer that occurs when a temperature difference gradient exists in the medium. I know that all just sounds funny. Temperature difference exists in a medium. A medium is an object. The energy could be an object. It could be a fluid as well, right? That's why they say medium. The energy is transported within the medium from the region with more energetic molecules, right? The energy is transported within the medium from the region with more energetic molecules. So that just says the energy is transferred from the object that is hotter to the object that is colder. All right. So that goes back to saying the object, it always flows from high to low. All right. So if you put two objects together and one is hotter and one is colder, all right. So the energy is going to transfer from the hotter object to the colder object. All right. The energy is transferred from high temperature region to a low temperature region. And what does that they mean exactly? It's just more or less like osmosis. It's from two things touching. All right. That's a mode of heat transfer by conduction. All right. And then there's a formula for that. The rate of heat transfer. The rate of heat transfer by conduction is given by Fourier's law. Right. And so heat transfer is Q, which is equal to Ka, which is A is the area, times T1 minus T2 over L, and that's the thickness of the material. And K is the thermal conductivity. And so you have different thermal conductivities for different materials, right? Which goes back what I was saying, my thermal conductivity, I have no idea what it is. But if I was trying to determine the rate of heat transfer of myself, right? And I put myself up against something that was hot, right? And I was cold, and then I began to get warmer. Or if I was hot, and I put myself up, I got in front of a fan, and then it began to blow on me, right? I would determine my rate of heat transfer by knowing my thermal conductivity. Now, seeing that we brought that up, let's do a problem. Finding a good old example.
Isn't it like if like you were to touch something hot, it makes you like hotter and then you cool it down, right? It's like a
Well, it depends on it will get cooler, but if it's a constant heat rate mode of heat transfer, such as a fan, the fan isn't going to get warmer, right? Or it's not going to get hotter. But what would happen is the room would get hotter. But if it's a large room, you're not going to see a temperature change, right? If you're hot and you go into an extremely large room, yeah, you're not going to see much of a temperature change. But if it's a confined space, if it's small and you're hot and you go into that space, then that space would get hotter because of you. Meaning like confined, meaning not a lot of room. Like if it's almost touching you, that room would get hotter. And that's it's a mode of heat transfer by conduction.
Oh, okay.
All right, so let's look at example 11.5. Example 11.5 in your book. This is chapter 11, looking at example 11.5. So you know what time it is. I get to show off my artistry. I know you guys are gonna miss it. I drew that little dimple there just for, for effect. It's just for effect. It makes it look cooler with the little dimple there. This little dimple here. Who wants straight lines anyway? Who cares about that? All right, so let's read it. It says calculate the heat transfer rate from a single pane glass window with an inside surface temperature of approximately 20 degrees Celsius and an outside surface temperature of 5 degrees Celsius. The glass is 1 meter tall, 1.8 meter wide, and 8 millimeters thick, as shown in figure 11.8. All right. The thermal conductivity of the glass is approximately K is equal to 1.4. All right. So we got our K, our thermal conductivity, and that's equal to 1.4. What are the units? 1.4. We got a W. What is that W? Nobody knows? Nobody knows. Oh, okay. So watt. So watt. All right, 8. Now L is 8 millimeters, which is equal to 0.008 meters. So then we got T1 and T2. This right here, MK. Yes, that is MK. M dot. Ooh, that didn't look right. M dot K. That M dot is just M times K. All right. So then we got T1. What is T1? It's 20 degrees Celsius. And then T2 is 5 degrees Celsius. All right. So what's the area? What is the area? Area of the pane, the window pane. What is the surface area of this window pane? (1.8 meters squared). That is correct. 1.8 meters squared. All right. And so that's everything, right? So then Q is equal to KA, KA, delta T. So T1 minus T2 over M. K. So M, what is M? It's just meters. K is Kelvin. So then that means you would have to convert your temperature to Kelvin. All right. So when you convert this to Kelvin, then what do you get? Nobody. Nobody remembers. Celsius to Kelvin is add 273. No. Right. All right. Let's do that. Yep. So then we would, as I say, it'll be equal. And so it's supposed to be an L, right? Let me do that. Let me do this correctly. So this was supposed to be L. So then when we plug everything in, we would have 1.4, and that's watt. What is a watt? Is it a joule second? Joule per second? Is that a watt? Let's just leave it as watt. Let's just leave it as watt. Watt, meter, Kelvin, times 1.8 meters squared times 293 minus 278 divided by L, which is 0.008. And that's meters. So okay, what do we come up with after that? So our Q, our rate of heat transfer is equal to what? $47.25 watts. That everybody got? It's just plug and play, right? Cancel the knowns. You got meter squared here. You got meter, right? You got your Kelvin here. That cancels. With that Kelvin, and then you're left with watts. And then that's what your answer is. All right. Pretty simple stuff. So then let's change it up. All right. So you say you have the same little window pane. It's a little thicker though. Only thing we're changing is this. Let's make that 2. Two meters is the thickness. And then the material, we're going to choose something different. Oh, interesting. I got a quantity in here for human muscle. So let's say this is human muscle. You know, it's kind of curvy, so it could be a muscle, right? You know, maybe a little bit. And let's say K is now equal to 0.41. 0.41, and let's say that is, wait, that's ugly, 0.41. Let's get that looking a little better. No, then I'll be like, let's get it looking better, and then it doesn't look better after I do it. That's horrible, right? That's just horrible. I'm focusing. I'm focusing. Uh-oh. Uh-oh. Wait. Almost. Uh-oh. So that's that's a watt, and that's a meter Kelvin. All right. Right off the bat, what does that look like? What does that say? The thermal conductivity of a muscle is a lot lower than the thermal conductivity of glass. So what is that? What do you think is going to happen? Just thinking about it before we actually try to solve this problem. Anybody? Nobody? No. Okay. So it's okay. So if you look at the thermal conductivity of a muscle as being so much lower than the thermal conductivity of glass, right off the bat, it should tell you that we're going to have a lower rate of heat transfer, right? Because a muscle does not conduct heat as high as glass does, right? So the change in temperature of your body is going to take a little longer than the change in temperature basically through a glass. If you have muscle, it's going to take a little bit more time. It's because the energy, the rate of conductivity is so much lower. It's going to take a little longer to heat you up. It's going to take a little longer to heat you up. All right. So, anyways, let's complete the problem. So A is the same. A is 1.8. Meter squared, right? T, delta T is the same. And it'll be 293 minus 278 Kelvin. And so what is our Q? We changed up that, right? So if we were to leave it the same, right, at initially, if we were to leave it at 0.008, just to leave everything the same, but our K, what do we get our answer to be? Remembering that Q is equal to KA T1 minus T2 over L. And so Q is equal to, what's the answer? Is your calculator's not working at this point? All you changing is 0.41, right? And you just plug in. What's what's the answer? Low participation. Y'all feel like, man, that test, we took this test, and then a lot of you probably was like, man, it was hard. And then some of you probably missed some stuff that you probably didn't feel like you should have missed. And so y'all mad at me. Don't you don't have to be mad at me. I mean, 6.15. Okay, so Lawson got 13 something. Uh, Z got 6.15. Remember, you're going to divide by the 0.008 initially, not the 2. So this would be 0.008 meters. All right, so it's going to be 0.41 times 1.8. Area is the same. We're leaving everything the same but the K. We're just changing the material. This is 293. Minus 278. Over 0.008. So Q is 2,400 watts. Is that what you got? Anybody else get that? Oh, 2490. 2490. So that rate is almost half of what it was for glass, right? It's almost half the rate. So it's taking a little harder to flow through that muscle. Taking a little harder, and it's gonna take a lot longer for that heat to change. Okay, it's gonna take a lot longer for that heat to change. All right, so it could be good and bad, right? Good and bad. So if you have muscle, you're gonna be a hotter person. You're gonna be a naturally hotter person, number one, too. But when you are needing to change temperatures, it's gonna take a little longer because muscle does not conduct heat very well, right? And so you got to think like passing through. So if you're needing something to conduct heat very well, right? Like a house or your oven, right? You're needing a material to conduct this heat faster, right? So you're needing it to heat up sooner, right? You're going to get something that has a higher heat conductivity or thermal conductivity, right? So one thing that conducts heat very well, basically allows it to just pass through, is aluminum foil, right? So you cook something on aluminum foil and heat just passes through it. You know what I mean? It's not very much of a barrier. It'll just heat your food. Um, so that's one medium that you'll want to use for heating up something. All right. Moving right along. So the next thing we'll cover is thermal resistance. Thermal resistance. Just the opposite of thermal conductivity. You want something that resists heat transfer. And so this is where we will look into thermal resistance. So thermal resistance. It's a insulating materials, right? It's a material that insulates. So obviously glass isn't going to be something you're going to use for insulating anything, right? You're not going to use glass. All right, you're going to use something else, something that has a high thermal resistance, something that has a low thermal conductivity, right? That makes sense. All right, and so to calculate thermal resistance, you recall Fourier's law. And so thermal resistance is just the thickness over the conductivity times the area. All right, the L divided by K times A. It's your R factor. All right. And then on other aspects of thermal resistance, you're going to have L over K, or your R factor. All right. Well, let's work an example though of this form of thermal resistance. Well, we'll just look over it. Let's just look. Oh, well, no, let's work it. Yeah, let's work it. Let's work it. I know, because you guys are being real quiet, not really participating. You know, I got 3 people. Nobody's talking. It's like, man, y'all been mad at me since the since your presentation, I guess. It's like, you made us talk. It's like, oh, my bad. I won't do it again. All right, so example 11.6. If you go with the glass, basically your thermal resistance, so your R prime, right? It was equal L over K times A. All right, we're using the same area, the same thermal conductivity for glass. So you'd be 0.008 meters divided by 1.4 times 1.8. And that equals, what does that equal? Right, 0.00317. Point 0.00317 kW. All right, and that's R prime. And then, so if we were to do the R value or R factor in glass plane, because it's 2. So you got R prime, you got R. So R is L over K. All right. And then that answer is just 0.008 divided by 1.4. And that's 0.00057 meters squared Kelvin per watt. That's your resistance. Okay. So if we were to look at this is the resistance for glass. So if we were to look at R prime for a muscle, L over Ka, which we already know that. Let's just put the numbers in. And you have 0.008 times 0.41 times 1.8. And that equals 0.011 Kelvin watt. You see how much more that is? Oh, so that's 0.41. Oh, that's a 0.41. Okay. And that's times 1.8. And so you get 0.011, right? That almost doubles the resistance of a muscle, almost doubles the resistance of glass if you're looking at the same area of the glass, same thickness of the glass in comparison to a muscle, right? It's just the thermal conductivity is so much less. So the thermal resistance, it's almost double, right? All right. So thermal resistance just goes hand in hand with it's the reciprocal, basically, almost not exactly the reciprocal, but when you're thinking about the resistance of a material, you think about uh, a lower thermal conductivity. All right, it's going to have a higher resistance for heat transfer. All right, moving right along. Now, the next thing you saw was on my slides was convection, and we'll end there for today. Heat convection. What is heat convection in your own words? Heat convection. We talked about conduction, change in temperature with two objects touching. So what would be convection? What would be the transfer of heat without direct contact? Yeah, that makes sense. Makes sense. But something is going to contact it, right? Because like even if you have a fan, right, that fan is blowing a fluid onto me. The fan isn't contacting me, but that fluid is, right? So what's making it happen? The fan, right? It's work. Work is making the transfer happen. So what would you call that? Yeah. Well, they both do in a sense, right? Because like conduction could be a change of temperature through a fluid as well. Yeah. Yep. But that's like we could say that for conduction. So what's boiling water in a pot? Yep. Yep. Because you're using an oven to boil the water. But would that be heat conduction or convection? Hmm. Is boiling water heat conduction or convection? I'm going to say it's convection, but I've been wrong before. Yep. So boiling water, it is a form of natural heat convection. So without further ado, heat convection. Per the book, it says it's a mode of heat transfer that occurs when a fluid in motion comes in contact with a surface whose temperature differs from the moving fluid. All right. So it's almost like it's saying with a stationary fluid, it comes into contact with a moving fluid, then that is called um, heat convection. But a heat sink would be more like a heat conduction. That would be conduction. Convection is the use of a fan, right? And so when I was in school, when I took heat transfer in my undergrad, what we called it forced heat transfer. It's forced, right? So that's the way to think about it. The fan is forcing the heat off of me versus two fluids touching, like versus me and something touching me, right? It's forcing it off. Like if you think about the wind blowing onto me, it's a moving fluid. That wind is moving. So that would be like a natural force heat convection. And it's like, why you say natural? Well, because the wind is blowing. It's not like a fan where I'm having to put, like electricity and all of that. Uh, yeah. Or even like boiling water, that's like more of a force because it's electricity or a gas stove, um, providing a heat transfer for the fluid versus you just allowing it to touch something that was already hot or a surface that was already hot, right? And then the sun would be radiation, right? So when you think about heat convection, you think about a fluid moving, but you also think about forced heat transfer. You're using something that's working, like a fan that's working, or a heat exchanger that has a moving fluid pumping through it, right? You got some kind of fluid, and it's like either using gravity that's causing it to flow, or you're using some type of pump to pump the fluid through to cool one fluid, right? And then you have like a fluid, what is that, RF31, like a refrigerant fluid. And so that's already a natural cooling fluid. And then you pass that fluid through uh, over or near a surface that has a warmer fluid, right? And then that would be also another form of forced heat transfer. All right. Hopefully, I didn't confuse you too much on that. Maybe so. It's okay. And I like this where it says free natural convection, where it says situation where the flow of fluids occurs naturally due to the density variation in the fluid. Um, or you can think about gravity, right? So, but they're saying density variation, something that's lighter versus something that's heavier of a fluid, right? Which like you think about a gas being like a lighter or less, the density is less than a water. Then you're using that natural transfer of the flow over the water to cool that surface of that water. But anyways, so then we have Newton's law of cooling, right? So for both forced and free convection situations, their overall heat transfer rate between the fluid and the surface is governed by Newton's law of cooling, which is Q is equal to H times A, T surface minus T fluid. All right. And then H is just the heat transfer coefficient. All right. A is the area. And then you have the temperature change. Also, I want to go back. Well, we'll cover it here. We'll cover it here. So let's look at an example for Newton's law of cooling, and we'll cover it. Cover what I have in mind. And so if we look at example 11.9, oh, wrong direction. So example 11.9 states, determine the heat transfer rate by convection from an electronic chip whose surface temperature is 35 degrees Celsius and has an exposed surface area of 9 centimeters squared. The temperature of the surrounding air is 20 degrees Celsius. The heat transfer coefficient for this situation is 40 watts per meter squared Kelvin. All right. So then you got this electronic chip. Right. And the area is 9 centimeters squared. All right, that looks horrible. H is equal to 40. And that's watts per meter squared. Kelvin. And then we got T surface, 35 degrees Celsius. And you got T fluid is 20. All right. And so what is the rate of heat transfer here? Q HA times T surface minus T fluid. And what is Q? Nobody knows. Nobody knows what Q is. Disclaimer. This is in your book, right? Example 11.9. Y'all can just say, oh, type it in 5.54 watts, right? Yeah. Y'all are asleep tonight. Y'all don't want to work with me tonight. Y'all ready to go. Y'all are ready to go. Okay. Well, we just got a couple more examples and I'm gonna let y'all go. Right. I'm gonna let y'all go. We got a couple more examples. All right, so Q is point. Oh, it's in your book, Cassandra. All right, so it's 0.54 watts. All you have to do is plug in everything here, right? So you got H, which is 40. You got 9 centimeters squared, right? And so you just divide that 9 by 100 squared. So that'll be 1,000. So you get 1, 2, 3, 4, or 1, 2, 3. You move it over 3 times. So it'll be 0, 0, 0, 9, or something like that. 3 zeros and a 9, something like that. So 100 squared, I think it's 10,000 or somewhere up in there. Yeah, it's 10,000. So you move this over 4 times. So you have 3 zeros in front of the 9. Plug that in for the A, 40 in. Then you have the 35 and you have the 20. This is what I wanted to bring up, right? So if I change this 35 to Kelvin, right? So it'll be 273 plus 35. What is that? 307-ish. Somewhere up in there, Kelvin. And then you have the 20, which is 293 Kelvin. All right. So when you work out this, you're going to get 0.54 watts. But check this. It's going to be the same if you leave it at 35 and 20. Right? 307 minus 293 is the same as 35 minus 20. It's 15 or whatever, or 308 or whatever that's should have been. Yeah, it should have been 308. Sorry. But anyways, it's 15. That's the difference. So what am I saying? I'm saying you're going to get the same results if you leave 35 in there. So that unit is really obsolete. And yeah, you still need to cancel out the K. So, but the difference is still going to be 15. So you can just cancel that K. Just wanted to point that out. But you're going to need to make sure you cancel your K when you're working this problem. All right. And so then your heat transfer coefficient is going to vary with the fluids. All right. So you have, if you're flowing a liquid, then you're going to have a higher heat transfer coefficient than with a gas. All right. And that's free convection. But if you look at forced convection, it's the same. You're going to have a higher heat transfer than with a liquid. So what does that tell you? So if you're losing a gas for heat transfer, forced heat transfer, right? It's going to take a little longer to cool it down than a fluid would, which is like the refrigerant, RF, whatever that is, 34A, RF431A, I don't know what it is. It's something like that. But yeah. But anyways, so if you're looking at a forced heat transfer, you're going to use a fluid with a higher heat coefficient to cool it faster. Okay. And then you have thermal resistivity. Is really just equal to R is equal to 1 over H. That's R. And so we were looking at that same problem. It would just be 1 over 40. All right. And then that would be 0.025. That is meters squared. Kelvin per watt. And that's your R factor. All right, any questions? All right. So that's all I have for the evening. On Thursday, we'll finish up with radiation. All right. Finish up with radiation. I know, fun stuff, fun times. Fun times in the meme lab. All right. Good deal. All right. Well, there's nothing else. You all are free to go. If you were wondering, the average for the test was like an 81. So yes, same thing you're going over in physics. This is good. So, but yeah, the average for the exam was an 81. That first exam, I think, was a man. I can't remember. It was either high B. I think it was a low A. It was a low A. I think it was like a 92. The first exam, the average for the first exam was like a 92. So, all right, everyone. You all have a great